if we look back at our work at investigating that dynamical system with roadrunners and coyotes, we might notice that the basis, 100, 300, and 200, 100, again, those were two different initial state vectors. Those actually form a basis of R2, and then we have A. But now the question is, what is this? What is matrix B if B is matrix A in B coordinates? Okay, well, we might have to unbury our knowledge from change of coordinates, but it ends up being that we can write B right as A V1 in the first column, and then A V2 in the second column. And if you were to do that out, what you would end up getting is 1.1, 0, 0, 0.9. Oh, this is interesting because isn't this those, remember I said we would see where the 1.1 and 0.9 came from? Well, that's interesting, okay? We can also look at the very first example that we were working at of 100 or 1000, 1000, and we can represent it in terms of the two basis vectors, right? So then if we look at x1, so if we were to step forward, we would have to apply matrix A, right, to this 2v1 plus 4v2, okay, right? It would be, we'd have to apply matrix A to our first step. Okay, that's fine. And okay, surprise, surprise, we can write it as 2AV1 plus 4 AV2, okay? And now here, this is going to be my claim, which you'll have to come back to. This is going to be the same as saying it's 2 times 1.1 V1 plus 4, 0.9 V2. Okay, so again, take that part on faith right now. We'll confirm it later. X2 is going to be, all right, so it'd be a squared of the first vector, or of our first initial state vector, 2v1 plus 4v2. Okay, so again, 2a squared v1 plus 4a squared v2, and now here this is my claim, prove it later. This is going to be 2 times 1.1 squared v1 plus 4 0.9 squared v2. So then based on these two, I might conjecture, at least for now, again we'll prove it later, that x of t is could be represented as 2 1.1 to the t power v1 plus 4 0.9 squared v2, and this is all assuming that we start with our initial population of 1000, 1000. Okay, so then in the last video we also looked at long-term behavior, like what would happen if we continued forever, forwards or backwards, in this case forwards. Well, if we look at this just from our knowledge of calculus, oops, and I miswrote this, that shouldn't be a square, that should be a t. As t goes to infinity, right, powers of t, okay, exponential functions, this one is going to die off, right, that's going to go to 0. So then really what's going to happen is that this should approach the line spanned by v1. Okay, and now why does this all work? Well, so again, you're taking a lot on faith right now. Why does this all work? This works out because we found two vectors, v1 and v2, with the following property. Okay, we say A, or if we have A as an n by n matrix and V as an Rn, a non-zero vector, then we call an eigenvector for matrix A anything where A times V is the same as this lambda times V, and lambda is what we call the eigenvalue. Okay, so we have to have this equality. Okay, this definition I cannot stress enough. This is absolutely critical. Okay, be sure to get this this down, and we're going to use this in the weeks going forward. So you're gonna see this whether you like it or not. Okay. Last example to round out this video. Okay, if we have this matrix A, which we've been working with for God knows how many videos now, we would say that for this matrix, we have 100, 300 as an eigenvector, and if we review our work, right, we have eigenvector 100 and 100, 300, and 200, 100, and 100, 300 is going to correspond to eigenvalue 1.1. Okay, and that's kind of interesting because it was first value in the basis and then first value there. That's interesting. And then 200, 100 probably going to correspond to 0.9, and actually it is true. .9. Okay, so for that matrix, we can say these are the two eigenvectors and their associated eigenvalues. Okay, now in general, how you're going to find these, you have to be given very nice matrices, or else we have to tell you. Okay, later on we will have different tools to be able to find these, but right now we have to kind of use this definition and verify it almost. Like, here are the vectors. Verify that these are indeed eigenvectors with corresponding eigenvalues, blah, blah. Okay, so that's one way, and we'll get some practice doing it by other methods.